Dear students, we can go through some selected questions of reaction mechanism for your coming entrance examination. We can go through the questions one by one. To get the answer, I will explain some theory part also. See the question, which of the following molecule is least resonance stabilized? To get the answer to this question, you have to know something about resonance. What is resonance? Resonance means delocalization of pi electrons. Resonance is delocalization of pi electrons. It is observed only in conjugated system. That is important point. So you have to know about a conjugated system. A group, consider the system CH2 double bond CHG. The group G connected to the double bonded carbon is said to be in conjugation. The group G connected to the double bonded carbon is said to be in conjugation only if atom of G connected to the double bonded carbon has this is group G. The atom of G which is connected to the double bonded carbon has a pi bond. Such a system is called pi-pi conjugated system. Another one, the group G which is connected to the double bonded carbon is said to be in conjugation only if the atom of G connected to the double bonded carbon has a positive charge. It is called positive charge pi conjugation. Another one, the atom of G which is connected to the double bonded carbon has a negative charge. It is negative charge pi conjugation, right? The group which is connected to the double bonded carbon is said to be in conjugation if the atom of G which is connected directly to the double bonded carbon has an odd electron. It is odd electron pi conjugation. Another one, the atom of the group G which is connected to the double bonded carbon has a lone pair. It is lone pair pi conjugation. To be treated as a conjugated system, there should be a pi bond, then single, then pi bond. It is pi-pi conjugation. Pi bond single, then plus charge positive charge pi conjugation. Pi bond, single bond, and atom which is connected to the single bonded carbon, single bonded, the atom which is connected to the single bond which is adjacent to the double bond. It has a positive charge, negative charge, odd electron or lone pair. These systems are called conjugated systems. So, you know about conjugated systems and resonance. Stability of a conjugated molecule, stability of a conjugated compound proportional to extensive delocalization, stability of a conjugated compound proportional to number of conjugate positions, or stability of a conjugated compound proportional to number of resonating structures. Or you have to remember that resonance stabilization is maximum. That is important point. Resonance stabilization is maximum in fully conjugated systems. This is the most important point to be remembered here. In the first compound benzene, benzene has 3 pi bonds which are in conjugation. Pi bond, single bond, pi bond, single bond, pi bond, single bond, pi bond, it is fully conjugated. Furan, it is also fully conjugated. It is fully conjugated. All these molecules are fully conjugated systems. They are extremely stable. They have greater stabilization due to resonance. In the last one, this compound it is 4,4-dimethyl cyclohexa 2,5-diene di-N 1-on. Here this system is not fully conjugated. There is no extensive delocalization. So, among the 4 molecules given here, the last one is least stabilized. The last one is least resonance stabilized. Option 4 is the answer. And also you have to remember one more point. Here this molecule has cross conjugation. Conjugation is not continuous. Such a system having cross conjugation is also less stable, or their resonance stabilization is somewhat lesser. So, among the 4 molecules given here, fourth one has least resonance stabilization. All right, fourth one is the answer. Fourth one is the answer. And fully conjugated, fully conjugated, fully conjugated, this is not fully conjugated. Extensive delocalization is not that much. Extensive delocalization in the fourth molecule is less than that of the other molecules. So, the last one is least resonance stabilized. Okay. Next is the increasing order of nucleophilicity of the following nucleophiles. This type of question is very important for your JEE examination. So you have to know about nucleophiles and nucleophilicity. Nucleophiles are species having greater, nucleophiles are electron rich species. They are electron pair donors. Nucleophiles may be negatively charged, or they may be neutral molecules with neutral molecules in which central atom has at least one lone pair. Molecules having carbon-carbon double bonds, compounds having carbon-carbon multiple bonds are nucleophiles. So you are familiar with the nucleophiles. And what about nucleophilicity? Nucleophilicity is the reactivity of a nucleophile. Or it is the ability of a nucleophile to donate its electrons to electron deficient carbon. That is very important. It is nucleophilicity is ability of a nucleophile to donate its electrons electron deficient carbon. You have to remember, among a negative ion and its neutral, among a negative ion and its corresponding neutral molecule, among a negative ion and its corresponding neutral molecule. Negative ions, negative ion has greater nucleophilicity. That means if you have OH minus, among OH minus and its corresponding neutral molecule water, OH minus has greater nucleophilicity than water. Among NH2 minus and its corresponding neutral molecule, NH2 minus has greater nucleophilicity. SH minus and H2S, SH minus has greater nucleophilicity. Down a group, nucleophilicity increases. When you consider nucleophilicity halide ions, fluorine, chlorine, bromine and iodine, down the group nucleophilicity increases, as the size of the atom increases, polarizability increases means as the size of the atom increases, polarizability increases means electron donating nature increases. This means that nucleophilicity increases. That means among halide ions, I minus is a stronger nucleophile than Br minus, stronger nucleophile than Cl minus, stronger nucleophile than F minus. Similarly, when you consider SH minus and OH minus, oxygen and sulfur are the elements of the same group. Down the group, size of the atom increases, polarizability increases means nucleophilicity, ability to donate electrons to electron deficient carbon is greater for SH minus than OH minus. And another one, across a period, across the period, size of the atom decreases. Size of the atom decreases means polarizability decreases means electron donating nature decreases. This means that nucleophilicity decreases across a period. When you consider the elements carbon, nitrogen, oxygen and fluorine, CH3 minus, NH2 minus, OH minus and F minus, all these elements carbon, nitrogen, oxygen and fluorine, elements of the same period, across the period size of the atom increases, polarizability decreases, electron donating nature decreases, nucleophilicity decreases. So here CH3 minus has greater nucleophilicity than NH2 minus has greater nucleophilicity than OH minus has greater nucleophilicity than F minus. Another point to be remembered, suppose you have acetate ion, consider these two ions, methyl sulfonate ion. This negative charge is conjugated with the pi bond. It has two conjugate positions. Here there is two conjugate position, two resonating structures. Here three conjugate position, three resonating structure. When you can compare the nucleophilicity of anions, nucleophilicity of the species containing, nucleophilicity of species having resonance, as the number of resonating structures increases, reactivity of such a species decreases means nucleophilicity decreases. So another important point, nucleophilicity inversely proportional to number of resonating structures. Nucleophilicity of the species having resonance, more the number of resonating structures, lesser the availability of electrons for donation. As a result, when number of resonating structures or extent of delocalization decreases, the nucleophilicity of a species where the negative charge is in conjugation with the pi bond. So, if you remember all these points, you can easily get the answer of the given question. The increasing order of nucleophilicity of the following nucleophiles. I think now you are able to answer CH3COO minus, two resonating structures, water neutral, the weakest nucleophile, CH3SO3 minus, it has three resonating structures, hence lesser the availability of electrons, lesser the availability of the negative charge. This species has lesser reactivity. Its ability to donate electron to electron deficient carbon is less. OH minus, no resonance. It has greater reactivity. Greater reactivity. So, increasing order means the least reactive one. Water is less reactive than, among acetate ion and methyl sulfate, methyl sulfate ion, the anion of methyl sulfonic acid, H2O has least nucleophilicity, then CH3SO3 minus, it has lesser nucleophilicity than CH3COO minus, lesser nucleophilicity than OH minus. That means water has least nucleophilicity, then methyl sulfonate ion, then acetate ion, then OH minus ion. So, B less than, C less than, A less than D. Option 1. This type of question is very important. Nucleophilicity related question is a question related to nucleophilicity will be there in your question paper. Very important. Here below are two statements. Statement 1, hyperconjugation is a permanent effect. Statement 2, hyperconjugation in a ethyl cation, that is CH3 CH2 plus, involves the overlapping of sp2 carbon hydrogen CH, overlapping of sp2 carbon hydrogen bond with empty 2p orbital of other carbon. See, hyperconjugation is a special type of electron displacement that can be observed in, that is arises due to conjugation of, I think all of you know these things. Hyperconjugation conjugation arises due to conjugation of sp2 carbon with sp3 carbon hydrogen bond. sp3 carbon hydrogen bond. Consider it is an alkene. It has an sp2 carbon. This carbon is alpha carbon. It has on this carbon is sp3. It has one carbon. It has carbon hydrogen bond. In such a situation, there is this is the pi bond of these two between these two carbon. When this type of sp2 carbon sp3 carbon hydrogen bond conjugation is present, there is a chance of overlapping of this sigma bond is getting overlapped with this p orbital. As a result, this bond is shifting to this carbon HCH. Here hydrogen atom, hydrogen is existing as H plus ion. Here there is a new double bond. This carbon is having negative charge. CH2 double bond CH, single bond CH2 minus. This type of resonance in which there is one carbon hydrogen bond is absent here, it is called no bond resonance. It was proposed by Baker and Nathan. It is Baker-Nathan effect. See, consider ethyl hyperconjugation is observed in, hyperconjugation is shown by all those systems where there is conjugation of sp2 carbon with a alpha sp3 carbon hydrogen bond. This type of electron displacement is observed in alkenes, alkyl carbocations, alkenes, alkyl carbocations, alkyl free radicals, alkyl benzene, etc. Carbanions does not show hyperconjugation. When you consider a species containing cationic carbon, this cationic carbon has vacant p orbital. This vacant p orbital is overlapping with this carbon hydrogen sp3 carbon hydrogen sigma electron, CH3 here, it becomes H plus double bond CH2, hyperconjugation. It is CH3, free radical, one unhybridized p orbital with unpaired electron. This p orbital is overlapping with one of the carbon hydrogen sigma electrons, one of the sp3 alpha carbon hydrogen sigma electron, CH3, CCH3, double bond CH2, it becomes H dot. Hyperconjugation is a permanent effect. Propene, in propene this carbon-carbon single bond has a length less than 1.54 angstrom. The normal carbon-carbon single bond length is considered as 1.54 angstrom. Here the bond length in propene, the carbon-carbon single bond length is less than 1.54 angstrom. This shrinkage is due to hyperconjugation. This is alkyl benzene. Here there is sp2 carbon, sp3 alpha carbon hydrogen conjugation, hence resonance, hence hyperconjugation operates. As a result, electron density at ortho and para position increases. Alkyl group, alkyl benzenes. When an alkyl group is connected to benzene ring, that group increases electron density of the benzene ring at ortho and para position. That is due to hyperconjugation. Or another important point, ortho para directing nature of alkyl groups is only because of hyperconjugation. That is to be very important. Hyperconjugation is a permanent effect. That statement is correct. Statement 2, hyperconjugation in ethyl carbocation. It is due to overlapping of sp2 carbon, overlapping of sp2 carbon with overlapping of sp2 orbital with a sp3 carbon hydrogen bond. This carbon is sp3 carbon hydrogen bond. Here it is sp3 carbon hydrogen bond, sp2 carbon conjugation. This carbon is sp2. This should be the carbon atom possessing the p orbital. sp2 hybrid carbon is in conjugation with the sp3 carbon. So hyperconjugation ethyl carbocation involves overlapping of empty p orbital of this carbon atom with the sp3 carbon hydrogen bond. So statement 1 is correct, statement 2 wrong, statement 1 is correct, statement 2 is false, option 1. Okay, next is the reaction of propene with HOCl proceeds through the intermediate. This is an example of electrophilic addition. When an alkene is treated with HOCl hypochlorous acid, CH3, CH double bond CH2, ClOH, the reaction takes place through the formation of cyclic halonium ion intermediate. Due to the plus I power of this methyl group, this bond undergoes cleavage readily because cleavage of this carbon hydrogen bond can produce a cationic carbon that can be stabilized by 3 hyperconjugative structures. When this bond is getting cleaved, the intermediate carbocation formed will be stabilized by more number of hyperconjugative structures. This bond cleavage produces secondary carbocation. Here there is no free carbocation, even though once this cyclic halonium ion is formed, this bond undergoes cleavage readily than this one. The cleavage of this bond, if this bond is getting cleaved, the intermediate is primary. So once this cyclic halonium ion is formed, by the approach of the nucleophile to this electron deficient carbon, this bond undergoes cleavage, resulting in the formation of this intermediate. It is then attacked by OH minus, CH3, CHOH, CH2Cl. The reaction of propene with the HOCl proceeds through the formation of CH3, CH plus CH2Cl, option 3. The correct stability of the following diazonium ions. Diazonium ions given here are before that you have to know this is benzene diazonium ion. Benzene diazonium ion is resonance stabilized. It is stabilized by resonance. Presence of electron donating group. When an electron donating group is here, electron donating group increases electron density around the phenyl group, which minimizes the magnitude of positive charge of the diazonium ion. For example, suppose the species has electron donating group, it is plus R group. It increases electron density around the benzene ring through resonance. Due to resonance, here there is negative charge at this carbon atom of the phenyl group, again resonance, increases electron density over the nitrogen atom having positive charge. Due to this electron density, intensity of positive charge on nitrogen atom is minimized. That stabilizes the species. Similarly, suppose diazonium ion is having one electron withdrawing group. This group is electron withdrawing. It is minus R group that induces positive charge over benzene ring, that decreases electron density around the benzene ring. As a result, there is electron deficiency over the carbon atom holding that N2 plus part. So this minimizes this decreases the stability of the diazonium ion. So remember, this is more than sufficient stability of substituted diazonium ions. Stability of substituted diazonium ions proportional to plus R effect. Stability of substituted diazonium ion proportional to electron density around the benzene ring, that is due to the presence of plus R group, or stability proportional to plus R effect, inversely minus R effect. Keep in mind these points. First one, benzene diazonium ion with OCS3 group, it is plus R group. Benzene diazonium ion substituted with a NO2 group, minus R group. Benzene diazonium ion and benzene diazonium ion substituted with the CN group, it is minus R group. Minus R power of NO2 is stronger than CN. So here most stable is para-methoxy benzene diazonium ion, or para-methoxy benzene diazonium salt is more stable than benzene diazonium ion, more stable than para-cyano benzene diazonium ion, more stable than para-nitro benzene diazonium ion. So stability order, correct stability order, A is more stable than, it is minus R group, so A, then C. Among this NO2 is strongest minus R, here some little bit weaker, so A more stable than, C more stable than, D more stable than B. A, C, D and B. A, C, D and B. Okay. Find out the major product from the following reaction. The given compound is hydroxy compound. that is treated with a concentrated sulfuric acid. You know that when a hydroxy compound is heated with concentrated sulfuric acid, dehydration product is formed. When an alcohol is heated with a concentrated sulfuric acid, elimination occurs, dehydration occurs. First step of the reaction, protonation of the alcohol. Lone pair of the oxygen atom is accepting a proton of H2SO4. First step, protonation of the alcohol. This protonated OH group, this protonated alcohol then removes water, giving a carbocation, In those reactions involving the formation of the carbocation, there is a chance for rearrangement either by hydride shifter, methyl shifter, ring expansion, etc. Then deprotonation occurs. Dehydration occurs. First is protonation of OH group alcohol. This protonated alcohol removes water, giving a carbocation. This carbocation is secondary. One of its adjacent carbon atoms is tertiary and other is quaternary. So methyl shift occurs, resulting in the formation of a tertiary carbocation. From this carbocation, it is the most stable carbocation that can be formed from the given species. Here, deprotonation giving an alkene, 1,2,3 trimethyl cyclohexene. Other possibility, here the product carbocation, when one H plus is removed from here, another alkene is formed. Among these two, the double bonded system having more number of alpha hydrogen, 3 plus 3, 6, 7, 9 alpha hydrogen. So it is most stable dehydrated product, most stable dehydrated product. So dehydration reaction, elimination reaction, alcohols undergo dehydration, proceeds through the formation of carbocation. Here another type of question that can be framed from this part is the various stages, the correct sequence of various steps during dehydration of alcohol. 1. Protonation of alcohol. 2. Removal of water to form carbocation. 3. Deprotonation of carbocation giving alkene. Okay. Next. Order of relative stability of the contributing structures. So, to find out the relative stability of the different canonical structures, to find out the relative stability of the different contributing structures, to categorize the different resonating structures on the basis of their stability, you have to keep in mind some points. One, first of all, you have to see neutral species with neutral species are more stable. For example, CH2 double bond CH, CH double bond CH2, it is pi-pi conjugated system. It is neutral. The charged species among these, first one, second one, stability order, one is more stable than two. First of all, you have to see, you have to try to find out the neutral species is present in the given resonating structures. That one is more stable. Second one, this species pi bond is having one electronegative atom, resonance in this direction only. Why neutral species are more stable? Always neutral species, neutral contributing structure has more number of covalent bonds. In all the resonating structures, number of sigma bonds are equal. So, the one with more number of pi bonds seems to be more stable. Here there are two pi bonds, here there is only one pi bond. So, this is more stable, 1, 2, one is more stable than 2. If you, these are the two resonating structures of carbanion of acetaldehyde. In both these structures, number of pi bonds 1, 1, sigma bonds are same in all. So, here negative, you have to see the position in such a situation. Resonating structures have negative charge. If resonating structures are having negative charge and same number of pi bonds, in such a case, stability can be compared by considering the position of negative charge. Resonating structures where negative charge is on more electronegative atom is more stable. Resonating structure in which negative charge on more electronegative atom is more stable, and one with a positive charge on less electronegative atom is more stable. Here this atom has negative charge, here oxygen has negative charge. Oxygen is more electronegative than carbon. So, this structure, contributing structure 2 is more stable than 1. Consider its contributing structure is due to pi-pi conjugation, this pi bond is moving to that oxygen. Here there is positive lone pair is getting shifted. In these two resonating structures, in the first one, positive charge is on oxygen, and in the second resonating structure, positive charge is on nitrogen. Among these two, oxygen is more electronegative than nitrogen. So, among these less electronegative atom nitrogen with the positive charge is more stable. Among these two, second resonating structure is more stable because their positive charge is on less electronegative atom. So, second one is more stable than the first one. Consider these two contributing structures. CH3OCH2 plus, its contributing structure is CH3O here. This atom has 6 electrons, incomplete octet, 8 electrons, carbon 8 electrons. Here carbon has 8 electron, oxygen is having 8 electron, carbon again 8 electrons. In these two resonating structures, the species having complete octet is more stable, even though oxygen atom has positive charge, it has complete octet. That means when electronegativity and octet rule are competing, octet rule has greater priority. So, here second one is more stable than first one. on the basis of these points. The first one is CH2 double bond CH, C double bond OH, that is neutral. It is neutral, first one. The second one, CH2 plus CH double bond C, O minus H. Third one, CH2 minus CH double bond C, O minus H. Can you give the stability order? First one is neutral. Second one, negative charge is on oxygen, positive charge is on carbon, negative charge on more electronegative atom is more stable. In the third one, this oxygen has positive charge, carbon has negative charge. Here positive charge is on more electronegative atom oxygen, so that is least stable. So stability order, one is more stable than stability of these contributing structures. Stability of these contributing structures, one more stable than, two more stable than, three. Option 1. The increasing order basicity of the following compounds. This type of question is very, very important for your JEE or advanced entrance examination. These are all amine nitrogen containing compounds. So, to get the answer, keep in mind the following points. The basic strength of nitrogenous compounds proportional to electron density over nitrogen. Basicity of nitrogenous compounds proportional to availability of electron density over nitrogen. Okay. And also you have to remember that primary amines, secondary and tertiary amines, always secondary amines are more basic. If nothing is mentioned, means the medium is aqueous. So secondary amine is more basic. See the compounds one by one. It is a primary amine. Nitrogen atom is sp3 hybrid. So that nitrogen is less electronegative. It has a tendency to donate electron. Second one, an amine of propionaldehyde. It is an amine nitrogen is sp2 hybridized. sp2 hybridized nitrogen is more electronegative than sp3. So, lone pair of nitrogen on sp2 hybrid, lone pair of electron on sp2 hybrid nitrogen is less available than that of sp3. Third compound is aminoacetaldimine. Here nitrogen's lone pair is in conjugation, resonance occurs. Due to resonance, one nitrogen is negatively charged. So, this negatively charged nitrogen electron is, this negatively charged electron is, this nitrogen is donating the lone pair to proton readily. In this situation, due to resonance, two equivalent resonating structures are possible. These two are two equivalent resonating structures. So, this species has greater tendency to donate electrons. It has greater basic strength. Fourth one, secondary amine. Nitrogen having lone pair is sp3 hybridized. So, among the 4 nitrogen compounds given here, since the third one can maintain two equivalent resonating structures by accepting a proton, that conjugate acid is more stable. So, third one has greater basic character than, then comes secondary, fourth one, then comes primary, then comes second one because nitrogen atom holding the lone pair is in sp2 hybridized. So, 3 increasing order means, increasing means 2 less than, 1 less than, 4 less than 3, 2 less than, 1 less than, 4 less than 3. Okay, very important type question. Nitrogen containing compounds basic character is very important. Increasing order of basicity for the following intermediates from weak to strong. These are all negative ions. In this situation, in such a situation, you can compare the basic character, basic strength inversely proportional to electronegativity of the carbon atom having the negative charge, electronegativity of the atom carrying the negative charge. That is enough. inversely proportional to electronegativity of atom carrying the negative charge. In the first one, this negatively charged carbon atom is sp3 hybridized. Second one, this negative charge is in conjugation. Conjugated negative, the carbon atom holding the negative charge. The conjugated negative charge, the carbon having the conjugated negative charge is sp2 hybridized. Then only resonance occurs. Third one, CH triple bond C minus. Here carbon having the negative charge is sp3 hybridized. CH3 minus, this carbon is sp. Here CH triple bond C minus, carbon having negative sp hybridized. CH3 minus, carbon is sp3 hybridized. Fifth one, Cn minus, C triple bond N, that is sp hybridized. Among these, this species, here carbon is sp hybrid, here also carbon is sp hybrid, but this sp hybrid carbon is bonded with an electronegative atom, so this electron is least available for donation, means that is least basic. Least basic one is 5. Least basic one is Cn minus. Then comes CH triple bond C minus. Then this is sp2. CH2 double bond CH2 minus. These two are sp3. Then comes CH3 minus. Then CH3 thrice C minus. So basicity order, increasing order. Fifth one is less basic than. Third one is less basic than. Second one less basic than. Fourth one less basic than first one. 5, 3, 2, 4 and 1. If some negative ions are given, in order to find their basicity order, basicity of species having anionic carbon inversely proportional to electronegativity of the carbon atom holding the negative charge, more the electronegativity, lesser the tendency to donate electron. That is important. That is the basic point. So Cn minus ion is least basic, then acetylide ion, then allylic carbanion, then methyl carbanion, and finally tert-butyl carbanion. Okay. identify product A and B. These reactions are chlorination reactions. Chlorination in the presence of sunlight proceeds through free radical mechanism. The given double bonded system has this carbon atom is allylic carbon. This carbon atom is allylic carbon. A molecule contains allylic hydrogen, then halogenation readily occurs there. Cl2 gets dissociated to form chlorine atoms. This chlorine abstracts this H dot, giving allylic free radical. It again with the Cl2 giving allylic chloride. Again we would here dihalo products are given. Again chlorine dot is formed initially, giving allylic, another allylic free radical. This one interacts with the Cl2, giving dihalo compound. This is allylic halogenation. A is this is a cyclohexene with the chlorine, halogenation, the presence of carbon tetrachloride. Reaction proceeds through the formation of cyclic halonium ion. Then anti-attack of Cl minus. The product of the second reaction is so the answer is product A is, product B is option 2 answer. Correct order of acid character of the following compounds is: first one is phenol, second one is para-nitrobenzoic acid, third one is benzoic acid, fourth one is para-toluic acid. First one, phenol, is weaker acid than benzoic acid. Among the benzoic acids given, presence of electron withdrawing group increases the acidic character of benzoic acid. Presence of electron donating group decreases the acidic character. So among the four compounds given, para-nitrobenzoic acid, nitro group has minus R power, So para-nitrobenzoic acid is most acidic here. Then comes benzoic acid. CH3 group decreases the acidic character of benzoic acid, but that is more acidic than phenol. So acidic strength. Second one is more acidic than. Third one more acidic than. Fourth one more acidic than first one. 2, 3, 4 and 1. And you have to remember, whatever may be the substituent at ortho to benzoic acid, ortho substituted benzoic acids, irrespective of the nature of the group, whether it is electron donating or electron withdrawing, such a ortho substituted benzoic acid is more acidic than benzoic acid and its isomeric form. That is what we call, that is due to ortho effect. So here the option is fourth one. Find out the major products from the following reactions. It is a double bonded compound. 2-methyl butanene. The given compound is 2-methyl butanene. It is treated with the diborane in THF and then with H2O2 bar OH minus. This reaction is, the reagents used here is diborane in TH4 and then with the H2O2 bar OH minus. One with the BH3 in THF, 2 with H2O2 bar OH minus. This reaction is hydroboration oxidation. Keep in mind the following points about hydroboration oxidation. Hydroboration oxidation is indirect method of hydration. It follows anti-Markovnikov addition. Very important point. No free carbocation is formed. During hydroboration oxidation, no free carbocation is formed, hence no rearrangement occurs. Here hydrogen is BH3 provides hydrogen as hydride ion, and H2O2 provides OH minus ion. CH3CH double bond CH2, BH3 is an electrophile. This pi bond is shifting to this electron deficient boron. Simultaneously, this hydride ion is attaching to this carbon, giving CH3, CH2, CH2, BH2. Here this hydrogen is provided by BH3. Hydrogen peroxide plus OH minus gives peroxide anion. This peroxide anion is then carrying out nucleophilic attack. This bond is getting cleaved. This OH minus ion is released. CH3, CH2, CH2, OBH2 plus OH minus, that is liberated from, that is coming from hydrogen peroxide. The nucleophilic attack of OH minus giving CH3, CH2, CH2OH. Overall result is addition of water. This hydrogen is coming from BH3, OH is coming from hydrogen peroxide. So, in this case, hydroboration oxidation, indirect method of hydration. Here OH is connected to anti-Markovnikov addition. This is the product of hydroboration oxidation of 2-methyl butaonine. Other reaction is an alkene is treated with a aqueous mercuric acetate and then with the sodium borohydride. It is oxymercuration, demercuration. About oxymercuration, demercuration, oxymercuration, demercuration. It is hydration, follows Markovnikov addition, another important point, no free carbocation, hence no rearrangement occurs. No rearrangement. No rearrangement. In the case of propene, when treated with the mercuric acetate and then with the sodium borohydride, hydration occurs according to Markovnikov's rule. No free carbocation, no rearrangement. This is the product. Propan, 2-ol is the product. Here the given alkene is two-methyl butadiene, oxymercuration, demercuration, Markovnikov addition, no free carbocation. So this is the product B. So answer is A is, B is this compound. So the option is second one. CH3, CH2, CH, CH2OH, CH3. Okay, this is the option. Choose the correct statement regarding formation of carbocations A and B. Butadiene is given. Butadiene HBr electrophilic attack H plus is the first step. This is one possibility. Other possibility, this bond is shifting to this side. There are two types of carbocations can be formed. Electrophilic attack H plus on alkene to form butadiene giving two carbocation. One is secondary, other one is primary. This secondary carbocation, it is primary carbocation. Among these carbocations, alkyl carbocations are stabilized by hyperconjugation. More hyperconjugation is present in secondary carbocation. So secondary carbocation is more stable. Primary carbocation is less stable. A more carbocation, a stable carbocation will be readily formed. So here out of the two carbocations, carbocation A is primary, carbocation B is secondary. Secondary carbocation is more stable, B is more stable, carbocation B is more stable than A, because that is secondary. A more stable species will be readily formed. So the answer is carbocation B is more stable and formed relatively at faster rate. Carbocation B is more stable than carbocation A. So, the more stable carbocation B will be formed relatively at fast rate. Right. Next is the decreasing order of hydride affinity for following carbocation. Hydride affinity means hydride ion accepting nature. Greater the hydride ion accepting nature means such a species has, such a cation has greater hydride affinity. Here carbocations are given. Carbocations are given. Among these, hydride affinity of the carbocations, inversely proportional stability of the carbocation. Hydride affinity inversely proportional to stability of carbocation. Greater the stability of the carbocation means lesser the tendency to accept the hydride ion. Here, among the given cations, you know that stability order of cations D is more stable than B, more stable than A, more stable than C. Hydride affinity D less than, B less than, A less than C, or C greater than, A greater than, B greater than D. C greater than, A greater than, B greater than D. Option 4. Among the given species, resonance stabilized carbocations are conjugated carbocations are resonance stabilized. The first one is conjugated carbocation, second one is also conjugated carbocation, third one is not conjugated, fourth one is not conjugated. So C and D are cations which are not conjugated, so they are not resonance stabilized. So among the 4 carbocations given here, resonance stabilized carbocations are A and B. Arrange the following carbocations in decreasing order of stability. This carbocation is secondary. Secondary carbocation, secondary having an adjacent atom with a lone pair, it is resonance stabilized. This is most stable. It is secondary. Presence of electron withdrawing group destabilizes the carbocation. So among the given cations, B is more stable than, because that cationic carbon has an adjacent atom with lone pair, then A, then C, or C less stable than, decreasing order. Question is decreasing order. So B is more stable than, A more stable than, C. Here B more stable than, A more stable than C. Okay. Next is polysubstitution is a major drawback in Friedel-Crafts alkylation. Benzene on treatment with the methyl chloride in presence of anhydrous aluminum chloride, methyl benzene is formed. The CH3 group is ortho-para directing activating group. So it reacts with the, it directs methyl carbocation towards its ortho and para position. This is what is meant by polyalkylation. Polyalkylation is a drawback in Friedel-Crafts. Polysubstitution is a major drawback in Friedel-Crafts alkylation. So in order to avoid Friedel-Pauli substitution during Friedel-Crafts alkylation in order to prevent polyalkylation in or poly substitution in Friedel-Crafts alkylation. Excess of aromatic compounds should be taken and reaction temperature should be low. So here poly substitution is a major drawback in Friedel-Crafts alkylation. Okay. What will be the major product in the following mononitration reaction? Consider a molecule having two benzene rings. In this molecule, this benzene ring is bonded to an atom having lone pair. A resonance occurs. Due to resonance, electron density this ring gets electron rich. This ring gets electron rich. It is electron withdrawing group. Decreases electron density around this ring. Here one benzene ring gets activated by lone pair of nitrogen and other ring gets deactivated by electron withdrawing nature of CO group. So here during nitration, nitronium ion is the attacking species. That nitronium ion is readily attacking to the benzene nucleus containing higher electron cloud. So here nitro group is connecting to the para position of this NH group. NH C double bond O, nitronium ion is getting attached to para to NH group, para to electron donating group. Here NO2 is attached. So the major product of this reaction is NH group activate the ring, NO2 is connected here, option 3. The major product of the following reaction is H plus ion, electrophilic attack, secondary carbocation is formed, to this intramolecular nucleophilic intramolecular pi bond transfer plus then deprotonation giving a compound having this structure product of this reaction is option 2 carbocation, then cyclization, special type, this is electrolysis reaction of potassium salt of a dicarboxylic acid during electrolysis the aqueous solution contains carboxylate anion. Under the influence of electric field, this carboxylate anions are moving towards anode. They release electrons, giving dicarboxylate free radical. This then removes carbon dioxide, giving carbon free radical. This then it becomes naphthalene. This is a more stable product of this reaction. What is the major product expected from the following reaction? Here this on treatment with the electrophilic attack of D plus, electrophilic attack of D plus produces a tertiary carbocation plus this is then this will do. This is sp2 hybridized, attack of Cl minus, DH ClCH3 plus DH ClCH3. These are the two major products formed, CH3 and D, Cl and H, CH3, H, D and Cl. Here two products are formed, other two are minor, major products these two. The major product formed in the following reaction is it is with HBr. Initially tertiary carbocation is formed. Normally we are expecting this tertiary carbocation that will be attacked by Cl minus. Remember, here cationic carbon is conjugated. So here cationic carbon is conjugated, hence delocalization occurs. Another primary carbocation is formed. Write down these two carbocations and write Cl minus here. Here Br, I think, Br. In this situation, you have to consider stability of both these double bonded system. This double bonded system has no alpha hydrogen. It has 3 plus 3, 6 plus 2, 8 alpha hydrogen. This is the major product. Here initially tertiary carbocation is formed. See that carbocation is conjugated, so delocalization occurs. It forms another carbocation. That carbocation has more number of, that double bonded system has more number of alpha hydrogen, so that product is more stable. In such cases where carbocation, even though that carbocation is formed, conjugated nature gives another form of carbocation. To this, among these, the one which is having more number of alpha hydrogen, double bonded system having more number of alpha hydrogen is more stable. So here it is 1,4 addition, 1,4 addition, product formed is CH3, CH3, double bond CH2 Br. It is 1,4 addition, option 3. The correct statement regarding nucleophilic substitution reaction in a chiral alkyl halide is racemization occurs in SN1 reaction and inversion occurs in SN2. A chiral alkyl halide, if SN1 reaction is taking place, then carbocation formed will be attacked by the nucleophile from either side. Racemization occurs in SN1 reaction and in SN2 reaction. Inversion occurs in SN2 reaction. Racemization occurs in SN1 and retention in SN2. Not correct. Correct statement. Retention occurs in SN1. Racemization occurs in both SN1 and SN2. So first option is correct. The decreasing order of reactivity towards dehydrohalogenation E1 reaction of the following compounds. Dehydrohalogenation resulting in the formation of alkene. During E1 mechanism, whether the reaction proceeds through whether the elimination reaction proceeds through E1 or E2 mechanism, more stable alkene producing alkyl halide is more reactive. Here it is E1 mechanism, elimination unimolecular. Reactivity, the one which can form a more stable carbocation can give this reaction readily. Here the carbocation formed is primary. Second one, carbocation formed is primary. Third one, carbocation is secondary. Fourth one, carbocation is allylic carbocation. So here the more stable carbocation is produced by D. So D is more reactive towards E1 dehydrohalogenation reaction. D more reactive than, then comes D, then comes B because that is allylic. Allylic carbocation is resonance stabilized. So D more reactive than, allylic B more reactive than, secondary more reactive than primary. D, B, C and A. Fourth one answer. Benzene on nitration gives nitrobenzene. This reaction is nitration. Electrophile is nitronium ion. You have to know that mode of generation nitronium ion. H2SO4 gives H plus and HSO4 minus. HNO3 accepts proton. HNO3 gets protonated, giving protonated nitric acid. Here HNO3 accepts a proton and acts as a base. Proton acceptor is a base. This then removes water, giving nitronium ion. So in this nitrating mixer, HNO3 acts as a base and H2SO4 acts as an acid. Okay. So some questions are discussed here from the topic reaction mechanism. All these are different types of questions. You have to go through these questions again. Okay. Wish you good luck. Thank you very much.
Brilliant Study Center, India's #1 coaching center for NEET and JEE.